Okay, thank you so much. I'm Muriel, and yes, I have on-campus parking, right? So basically, I'm on leave from MIT here. I lead the network coding. I've been leading the network coding and reliable communications group in the research lab for electronics. I'm a full professor in the electrical engineering and computer science department and hold the NEC chair for software science and engineering. It's a School of Engineering wide chair. I'm going to talk about Optimum. I first always like to recognize our backers, led by 1KX. And then let me go straight into what do I mean by memory. So what we mean by memory is basically, if you really are going to think, and you know, this is basically an ETH event, that Web3 is the world's computer, decentralized, and so on. And then you think, okay, you know, when I put together a computer, what things did I put on the computer, right? So other than if you're my son and then it has these lights so that it looks like it goes fast, in which case, you know, you're on your own. You basically have the processing part and you have the memory part. We'll talk a bit more about that later. And what we do is the memory part. And memory means anything where it's the data itself, not the compute part, but the data itself. Whether it be basically the ephemeral memory, the data propagation, that's Optimum P2P, that's our first product, and I'll be showing you some of the results from our hoodie testnet there. Whether it be the read-only memories, such as the ledger, which is basically the historical state. It's like a read-only. You add to it, but you don't modify it. Or whether it be the actual state, which corresponds effectively to the random access memory, the read-write, and doing that in a decentralized fashion is doable. But is not easy unless you have the right tech. And we'll go a little bit into what that right tech is. So this is what we mean. We're doing the memory. And again, when you think about putting together a computer, it's not the same folks who are writing your operating system, who are making your CPUs or your GPUs or whatever you're using, and who are making the bus and the memory. It's not the same people because it requires specialized expert knowledge and specialization in what you're doing. Okay, so let's go back to this idea of the computer and let's put a little bit more thought and structure around it. So on the left-hand side, I have the Web3 stack. Now, you know, different people have somewhat different layers in there, but I think pretty much everybody would agree that there are at least these layers, right? And we can talk afterwards if you want to stick other layers. I'm happy to do that. And what I'm doing here is separating the green layers, which are basically really around the computation, from those purple layers, which are really about the data. Okay, and the networking is about the data and it's about memory. It's treasured memory. Okay? And if we think, okay, how does this actually relate to a computer? Well, we can go back to what's called the von Neumann or the Princeton model, and you know, it came out basically right after World War II when people had done things like the Enigma machine and so on. They were really starting to think about what is a computer. And von Neumann said, well, basically this is the pieces that a computer should have. It has an input. It better have some way for me to tell it what to do. It has an output. It has to tell me what it did. And in the middle, there's the compute part. Let's think of that as the central processing unit, which has the control, say the EVM. It has the actual hardware, the arithmetic or logic unit, sometimes called ALU. And then it has what we would recognize as the bus to transport stuff, and the memory unit. And that's it. That's a computer. And this has stood the test of time, right? I will argue that any, you know, whether it be your phone, whether it be anything that you have, is actually abiding by that general structure. And again, there's variations on this, but by and large, it has stood this test of time. Okay, let's look at the top. Let's look at the green part. You have the OS, maybe an EVM, maybe an SVM, maybe whatever you have. And then you have applications running on those OSs. That part, if you look at the Web3 part and, let's say the classical single computer part actually looks fairly homomorphic. Okay, yes, there's all kinds of subtleties and so on, but it looks pretty recognizable. It doesn't look weird. Let's look at the bottom part, the purple part. That is not looking recognizable, right? You have very ad hoc solutions for read-writes, like mempools, right? Does your computer does anybody here have a computer that has a mempool in it? I hope not, otherwise let's talk. You have these giant full nodes for archival information. Instead of actually reading the data, those nodes are so big that you have to check that the data is available, which is DA. Your computer actually has something like that behind the scenes, but you usually don't display it. And then the part of the bus, particularly if we're talking, say, in the Ethereum context, and this has been, of course, in the news a lot with P2P and so on, is actually gossip, which is definitely not what's happening inside your computer. Okay. So with this framework and this sort of, intellectual discipline of, we should look at what a computer does. It doesn't mean you will never do something different, but it means if you're doing something different, you should have a very good, explicit, thought out, explainable reason why you're doing something different, okay? We basically look at the transit memory, the DRAM, and the DROM, which is basically the read-only memory. And what I want to look at mostly today is the Optimum P2P, which is basically the ephemeral memory, the bus, because that's our first product. Why does it make sense that it's first product? It makes sense it's first product because, by the way, you need to access the memory. So if accessing the memory, if your I/O to the memory is slow, then who cares how good your memory is? That becomes your bottleneck. So it makes complete sense. Okay, so you can say, okay, this is very nice, this is conceptual, but how are you actually going to do it? So recall that I've been leading the Network Coding and Reliable Communications group here at MIT, and I am by trade, by training, an information theorist. So we're going to use information theory, and in particular, we're going to use coding, and in particular, we're going to use a type of coding that I've co-invented here in my lab at MIT called RLNC. Now, this does not just, roll off the tongue, but it's actually very simple. The idea behind memory is that you're representing data, right? You have a data representation which can be recoverable. How do you make data representation be robust and efficient? You code, which means that you represent the data not necessarily as the original data, but you represent it as equations. And those equations can be invertible, have to be invertible, so that you can recover the data. And the way that we're doing this set of equation constructions is that we're using a linear approach, which is random, and the randomness critically has to work over a particular type of finite fields that are sufficiently large, that have a large enough cardinality that this all works out. And we have tons of papers. This work has won tons and tons of awards all over the world. So it's obtuse, but actually it's really intuitive. You're just going to make these equations, and these equations are infinitely composable. So because it's random, it's inherently decentralized, and because it's random, it's infinitely composable. I like to joke that when I started working on this, my colleagues would do wellness checks on me because they were like, why on earth are you working on this decentralized stuff, Muriel? Like, nobody gives your own word there, right? And basically I was like, but because it actually is amazing that you can do things in a decentralized way here, and this is why we're called Optimum, in an optimum way, even though it's decentralized. And my mind was so blown, I couldn't stop working on it. And this is what it does. So this is for Optimum P2P, so the a protocol called Optimum P2P, which you see up there. This is our live hoodie testnet. This is just a snapshot. Up top, you see basically how long we're taking in this particular time. For the latency, you see it's around 150 milliseconds. And on the bottom, what you're seeing on the y-axis, on the ordinate, is the number of times, how many x were better than the best node with current libp2p gossip sub, the current approach taken by Ethereum. We're 6 times better. Sometimes we're more. I don't think we've ever seen us go under 4 times. Okay? That's what it does for you. So a little bit of math goes a very, 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 very long way. So we've gone to validators with this because validators like things to go fast. MEV, increasing their APY. This is what they're trying to do. You know, the calls are always risibly short because we have like some really long presentation and about, 3 slides in, they're like, I get it, just give it to me. Thank you, Muriel, I don't want to hear your presentation. And basically, this is how we've been signing up in our private testnet, the hoodie, you saw the Grafana dashboard there, because it goes fast. So basically, this is where we are right now in terms of our node operator partners. And they've been fantastic. They give us, I have to say, that's something I've really, really appreciated in this community is the level of openness, intellectual curiosity, and collaborative, collegial approach. And our validator partners have definitely embodied those qualities. So who benefits? Well, obviously the validators, as we just said, L1s and L2s, we have also signed a few of those. And in the end, of course, end user dApps, et cetera, because, things are going faster, gas fees are lower, without using, using math, not using extra hardware. So with that, I'd like to make a plug for people who are interested in coming on Sunday here at MIT to our hackathon, where you will actually hack what we call a flex node, which is a node that's actually propagating those equations. And you can start seeing some of these benefits yourself. So if you have no plans for Sunday, or even if you have plans for Sunday, I think we have a couple spots left. Catch somebody with an Optimum hat or an Optimum shirt. There you go, there and there. And the jacket, and, see about registering. And, you really have to do it to basically see what it does and see what it can do for you. And with that, I shall stop and leave it for questions.
Yes, thank you. That's great. A quick one. Are there any other bottlenecks currently that would stand in the way of achieving the 6x? Like, what else is out there to block that at the moment?
Yeah. So what's out there to block that at the moment is basically the current way in which gossip systems operate. And I can give you a very high-level view of why this is. So what gossip does, it's decentralized transmission of messages. So suppose that I basically have some messages and I send them here to the first row and then they start sending them, et cetera, et cetera. Okay. If a node, say, gentleman in the second row is a node, and he doesn't have enough messages coming in, he's not going to be able to send it to the third row, right? Or it's going to take a while. On the other hand, if a node has too many connections, then what's going to happen is you're going to get a lot of duplicate, and that's going to clog up your network and create congestion. So in the P2P, there's a really subtle difference between those two effects, and you're basically trying to, enhance one without going, they enhance the connectivity without going too much into the congestion and the problems that that raises, okay? What we do is we send equations. Every equation that you get, pretty much, is going to be useful. So you don't get repeats. That's it. You don't get repeats. So you're like, yeah, absolutely. Just give me your equations. The chances that I get an equation that's not useful is almost nil, right? This gets back a little bit into the math. So it's really around the design, the protocol, and the math. Oddly enough, this optimum approach, and actually, my former student, Bernhard Hoppler, who was a student here, he was my PhD student, then he went to CMU to be a professor in computer science, proved what's called basically optimum. He showed that this approach, RLNC, achieves basically the same behavior, it's optimum pipelining, as though you had an omniscient centralized controller that's seeing everything and is actually telling everybody when to go. Okay? So this is the thing. It's not that going back to what I was saying, why I couldn't stop working on this, it's not that you go, okay, well, I decentralized, so I'm going to have to put up with all of this, inefficiency. The decentralized approach without state information does as well as a centralized approach with full state information, which is mind-blowing, right? It is mind-blowing. I don't know. That was a really long answer to your question, but I hope it was at least an answer. Yeah, absolutely. Yes. Oh, somebody has a mic. Whoever has a mic, sorry, I think.
I do.
Oh, sorry, yeah, yes.
So you had said that earlier in the presentation that there was supposedly like a minimum size for these equations to be able to encode information properly.
Minimum size of the field representation.
Yes. So in terms of some sort of byte or binary representation, what kind of like?
Oh yeah, it can be very small. That's a good question. So basically, you don't have to go to, say, primes, if that's the way your mind is going, which is a natural way to go if you think in finite fields. An extension field, even just of a binary, will work, right? So rough rule of thumb is the cardinality of the field. Take the inverse of that. That's the probability that one of your equations ends up being, to our discussion before, a repeat, which is not the end of the world. It's a little bit, right? So if you have, say, 8 bits, right, the probability that you get a repeat equation is, 1 over 2 to the 8, which is very small, right, compared to the probability before where you had tons and tons of it. Does that answer your question? Thanks. Yes.
Great presentation. It's good to
Thank you.
actually see someone working on this memory bottleneck that Ethereum always had. After the upgrade, I think in 2023, the Shanghai Capella upgrade, you saw many people having issues like liquid staking with all the transactions being stuck on the queue. I was one of them, had my transaction stuck for a few days. Yeah, so it's good to actually see you have something on a testnet.
Thank you.
When is the mainnet?
Oh, very good question. So, I'm hoping at the end of the year, Q1. I think Q1 is fairly conservative. Yeah. Thank you.
Let's give a round of applause.
Thank you.